Okay, this time I'm going to give an introduction about Sig-Scheduling, and this is Klaus, the co-scheduler, co-leader of Sig-Scheduling. Yeah, and this is
Hi, my name is Shivram, and I am one of the co-owners of Poseidon project, which is currently under Kubernetes 6. So I'll be talking on the Poseidon part, Poseidon and Firmament side. So, but I will be giving the intro on the general scheduling stuff.
Okay, so this is the chart of the Sig-Scheduling. I copied from our chart page. I highlight something is here. In the Sig-Scheduling we do several things, but the major target of Sig-Scheduling is to make the pod placement decision. And there are also several other things such as resource quota and controller, something like that. This can be at least officially it is out of scope of Sig-Scheduling, but we are also interested in this part. So if they're related to Sig-Scheduling, you can discuss with us. But officially we focus on the pod placement decision in the Sig-Scheduling part. And this is the overall of our Sig-Scheduling. Generally, we have two meetings. Now, the first one, I think this is more friendly to the Europe and US, and another one is more friendly to the Asia. So, if you are interested, you can choose the meeting to join us. And we have two leaders for each Sig. And the first one is Bobby. Okay, yes? Yeah. And another one is me. Yeah. We also have Slack. We also have mail list, and the other link is our issue. So if you have any interesting want to contribute, you can pick up some issue or submit a pull request. And we are also open to join our Sig meeting to show your proposals or your idea or something like that. And for the Sig-Scheduling, we have in the past few years, we initiated several sub-projects here. Now, for the Sig-Scheduling, the major scheduler is the Kube scheduler. This is the default scheduler in the upstream, and we also incubate several other things. Now, the first one is Kube-batch. Kube-batch is a kind of batch scheduler focused on to run such kind of MPI, TensorFlow, something like that. Another one is dscheduler, which help default scheduler to make a rescheduler of the current running pod. Another one is Poseidon. They try to use a different algorithm to resolve the problem, to resolve the pod placement department. I will give an OR of each one, so you can have an overall of our six. Now, the first one and the major work of Sig-Scheduling is the default scheduler. The default scheduler will try to do the scheduling pod by pod. We have a queue here. And we try to find the best pod for the best node for the pod to place. This is the major target of default scheduler. So we have two major phases. Now the first one is the predicts. We need to make sure the node match the basic requirement of pod. For example, some node selector, some node affinity, something like that. We will filter out the node not meet my requirement. This is predicts phase. Another one is the priority phase. We already filter out node 1 and node n. So for the node 2, 3, 4, we will find the best one. We have several policies here, such as impact, something like that. We will find the best one. So in this case, the node 3 is have the high score here. So we will put the pod in the node 3, right? So this is the default scheduler. And we also have a deep dive session tomorrow. So we are going to have more feature, more detailed about default scheduler for this part. Yeah. The second one is Kube-batch. the Kube-batch is focused on the batch scheduling part. For the batch scheduling, there have several requirements to the scheduling, such as gun scheduling, maybe fair share, something like that. So in this page, we can see that the target workload of Kube-batch is Paddle, TensorFlow, Spark, or something like that. And we also clarified the out of scope of Kube-batch because Kube-batch is only a scheduler. We will not cover the job management, data management, something like that. This is going to be out of scope of Kube-batch. Yeah. This is the overall architecture of Kube-batch. We have a cache to in the Kube-batch to dump everything from the test server, and we will make decision to have a loop to make a decision for every job. Yes, we in default scheduler in Kube-batch we introduce a kind of job information. We will do the scheduling in job level, such kind of that, and we have a session to have a dump of the cache to make sure there are no lock. Yeah, and we have predicts, allocate, preemption, something to do to make the schedule decision for a job. Yeah. This is a list of features. The major one is cross scheduling. That means if a job if a job have several pod, if this pod will going to be scheduled only everyone get enough results. If, for example, if you have two pod and each one required two CPU, and if we will make sure both of pod get 2 CPU, so then they will get started. If there any one of them didn't get enough results, both of them will be pending. Yeah. So this is a requirement from the distributed training of AI workload and MPI job. So yes, they need to start together. And we also have some other pending requirement. Some feature are have implement and something are not. For example, we would like to have fair share. Yeah, fair share across namespace, fair share across job, yes, job queue, something like that. And we are going to support job level preemption. Yeah, so we need to preempt the whole job to release the results for the high priority jobs. And task priority within job, something like that. But queue, I think queue is a common concept in the batch system, a batch scheduler. So we try to introduce a queue, and for now we didn't define the relationship between the queue, namespace, and maybe tenants in the future. So anyway, the queue part is depending here. Yeah. All of this idea, we have a issue. Yes, bring batch capability into Kubernetes. This is the issue ID here, issue number. And for now, we focus on the batch scheduling part. And in this issue, we also have some other parts, such as job management, and maybe node, not topologic or something like that. But in Kube-batch, we only focus on the scheduling part. We may have discussion or maybe have some separate project for the other part. Yeah. This is the user of Kube-batch, and we have Baidu. This is the company in China for search, and TuSimple is TuSimple is a startup focused on the AI workload, and we have some other companies to use the Paddle. I think we also have Vivo. They're also using Kube-batch recently. Yeah. Okay, this is the Poseidon part. Yeah.
I actually had a different set of PPTs, so I thought like I'll have a longer session. So anyways, I'll try to skip some of it. Like I'll try to keep it. So yeah, just to give a preamble of what Poseidon is, it was a university collaboration project which we started with the Cambridge University, and we ended up incubating that in a Kubernetes 6 repo. So they already had a scheduler called Firmament. So Poseidon is basically the integration part between Kubernetes and Firmament. So essentially, it is a centralized scheduler, and since Kubernetes now supports multi-schedulers, we have the capability to run, more than one scheduler at a time. So yeah, it has extremely impressive throughputs, and the resource utilizations are much better than the other schedulers. So I will not go through the limitations. So I will just briefly go through the design. So this is the integration design of Kubernetes and Poseidon and Firmament. So Firmament is essentially written in C++, where all the actual scheduling happens and all the scheduling logic is written there. So Poseidon essentially is a kind of broker who actually understands the Kubernetes objects, and he actually sends them to Firmament, and then Firmament actually builds its own structures, converts. Poseidon does the conversion, so Firmament essentially actually builds the graph and other things, and he tries to solve the graph. So yeah, so initially we had Heapster, but after I think sometime Heapster got depreciated. So now what we have is instead of that we have something called we have written our own informer. So basically it will listen to all the pods that is not created by Poseidon, so that that information is actually required for the scheduler to actually do a scheduling properly, in the sense, if there is some other scheduler running and if it has scheduled resources, then the other scheduler which is not aware of that pods that is being scheduled can actually mess up with the resource calculations. So we have wired that, and Poseidon and Firmament they actually communicate via gRPC services. So there is a Firmament service, and so essentially they both run as deployments in Kubernetes, and yeah, you can even run them as a systemd on the control plane if you like. So this is yeah. And this is the internal of the Poseidon design. So essentially it is the same thing, like we have the API server, we have the Firmament service there, and this Poseidon has a couple of things, like we call them as node watcher and pod watcher. So essentially that gets the information from the Kubernetes API server, like how many nodes are added or getting updated, if there is any updation happening on the nodes, labels and things like that. So those informations are actually passed on to Firmament. And similarly, when a new pod arrives, those information, if the pod has to be scheduled by Poseidon, those information will be actually captured by this pod watcher, and it will be sent. And yeah, so that Heapster part is so that is the utilization stats which it sends to Firmament. We initially had a Heapster sync which actually was sending the information to Firmament, but yeah, currently we don't have that. So that schedule loop is the actual. So Poseidon doesn't actually do a continuous scheduling like the default scheduler. So it is like we have a time interval. So the minimum time you can actually ask for to schedule is like 1 second. So max we have tried till 10 seconds. So based on your use case, you can say. So it actually groups and then schedules. So it is not a continuous scheduling. So that scheduler call is again a gRPC call which is actually triggered from Poseidon. So that is what is there. And yeah, so the internals of Firmament, I will briefly explain what it is like. So what happens is whenever the pods and because in this case all this pod and node watchers actually send the pod and the node information to Firmament and via the gRPC call. So when it is received, it actually we have a module called the graph manager. So the graph manager is essentially the manager, the module which actually builds the graph. So I will get to the graph. Then he calls the graph solver. So essentially the graph solver gets the graph that is built by Poseidon, and he solves and gives back the deltas. Gives back the placement information, and that is what we send back to Poseidon, and then Poseidon actually calls the bind call. So to explain the graph, I will. So yeah, so this is this slide should have been here, but yeah. So this basically Firmament actually solves the scheduling problem by modeling the task placements as a constraint based on a flow graph network. So it uses min cost max flow algorithm to solve it, and so it is basically based on the cost and capacity. I will explain you with a simple example. So let's assume that there are two tasks, T11 and T12, in the Kubernetes native thing. It can be assumed as pods. So there are two pods like T11 and T12 coming in, and we have two nodes, the M1 node and the M2 node. Okay, before that, this sync and this UA, so the flow graph has certain properties which says like the flow that starts from the source should actually reach the sink. So we actually make sure that whatever task comes from the source all meet at the sink, otherwise the flow graph is not complete. So that is one of the constraints that they have on the flow graph, and so if a task cannot be scheduled, so we have to anyways route it to sync, so we route it via this unscheduled aggregator. So we have two pods, this T11 and T12, and say let's assume that these two pods have the similar mem and CPU requirement, like 2 CPU and 2 MB of memory. And this one also has 2 CPU and 2 MB of memory. So what we do is we try to create a EC. So this is what we call as equivalence class, and we try to aggregate these two tasks into one task. So the only difference, if you see between the Quincy model and the Firmament model, is they didn't have the this equivalence class. So what happened was it ended up connecting more arcs. So more the arcs, then the time taken by the graph solver is more. So this equivalence class tries to, equivalence node, class node actually tries to reduce the number of arcs. Thereby it is more efficient than the Quincy's model. So I think that was their thesis on Firmament. So here what we do is, so here we have two nodes, M1 and M2, and we found that T11 and T2 will have the same requirement, and then we aggregate them into one task EC. And then what we do is, before the flow graph manager actually goes and he filters out the nodes. So this filtration process will actually go through all the predicate steps that is followed in the default scheduler. So he will actually go pick, he will pass through all the predicate functions, and he will filter out all the nodes from the list of nodes that is available, and he has actually found two nodes, M1 and M2, that actually fit this task EC's requirement. So then what he does is he actually, the flow graph manager will have to give the cost to the arcs. So now what he does is this M1 and M2 have a resource limit of 4 CPU and 4 MB of memory. So our input task EC has a request of 2 CPU and 2 MB of memory. So it again creates two virtual nodes called the machine ECs. So machine equivalence classes it creates, and each through this machine equivalence class only one task can flow. So similarly here, if you see, M2 has 6 CPU and 6 MB of memory. So it ends up creating 3 machine ECs, because the task EC's requirement is 2 CPU and 2 MB of memory. So then what it does is the cost function, after it has created, shortlisted, and after it has created all the machine ECs, it actually goes and calls the cost function. So cost function is where the actual policy or the scheduling policy of the Firmament is applied. So you can have different cost models based on your requirement. There is an interface which you can use that and implement using that. So here we have used a model called CPU and mem. So based on that cost model, he is actually assigning. So if you see this arc, it is cost, capacity, and min flow. So we don't use the min flow. It is because the open source solver which we use, CS2, doesn't actually support min flow. It supports only the cost and capacity. And anyways, the min flow max, this thing algorithm is actually based on the cost and capacity. So we don't require that. So this cost is actually assigned by that function, the cost function. So it says 100 for this, and it says 200 here, and it says 150 for this, 250 and 350 for this. So now after this graph is built, when the actual loop is called, when the schedule loop is, the schedule call is initiated, the gRPC call is initiated from Poseidon, what happens is the solver solves. So this is how he solves. So he actually sends the task, that is T11 pod to machine M1 via machine EC1, and task 12 to machine via to machine 2 via machine EC2. So if you see the cost, he has actually chosen the least cost, because this was 200 and this was 150. So least cost, and by this we also achieve node spread, in the sense we don't have to have a separate priority kind of thing to actually manage the spread of tasks across the nodes. So this also does both the things. So that is how the cost is actually assigned. So it all depends on the cost function. So this is like the brief thing. So if you want to actually you start using Poseidon, we are there on GitHub, and these are some of the references. Kubernetes 6/Poseidon, and the Huawei GitHub has the Firmament code, and those are the blogs. So if you want to create a pod and you want, if your default scheduler is also running and you want your pods to be scheduled by Poseidon, then you need to give this under the spec called scheduler name as Poseidon. And yeah, so these are some of the benchmarking. So we did, of course. So what we found is we wrote a couple of simulators as well, just to test the scheduler code. Not with the API servers and other things. So we have tested it till 100,000 nodes and 300, 400,000 pod workloads. It actually gives a throughput of about 30k pods per second, but that is not with the entire Kubernetes ecosystem in picture. So, but these are the results which we got from KubeMark testing, and we have also used scheduler perf in some cases. So you can see as the number of nodes increases, the default scheduler actually performs bad compared to the Poseidon scheduler. It is almost kind of consistent, or there is a slight deviation. So, but yeah, so the default scheduler is good. Till 5k nodes. I think beyond 5k only the problem lies. Otherwise, default scheduler is much better in various other cases. Like we also implemented this affinity cases. Like initially when we started off with the project, we didn't have all these policies that was available in default scheduler present in Firmament. So we built the pod affinity, node affinity, interpod, anti-affinity, and other cases. Then what we found is, I think after some time there was some huge changes in the default scheduler. So after those changes, like default scheduler is actually doing much better numbers than Poseidon in affinity and anti-affinity cases. So that's one thing. And we also have support taints and tolerations and other things. Yeah, the volume support is not. We don't do dynamic volume provisioning at present. It is not there. So we just do a simple, the already pre-bounded one. So yeah, I think roadmaps. Yeah, I think this is. We have to, like, co-location interference is one of the things which the original authors were actually more concerned, and they were actually developing Firmament for. Towards that. And so what is co-location interference is like, so if you have a two types of jobs running, and one job is actually hogging the CPU and he's using the underlying cache more, the rate at which the cache misses happen to the other job is more, and you need to find a way to actually place these jobs on different nodes. So that was their this thing, but I think we need a lot of support from at the kubelet level, and probably at the metric server level, to understand like what kind of tasks are running. So that was not implemented like in our thing. And also, most of them they were asking like whether Poseidon does the global rescheduling thing. So we don't actually do the rescheduling of the current task. I think that was the question they asked. So that was actually a tricky thing to do because we don't create pods. We only schedule pods. And the pods are created by the controllers. Basically, the replica sets, the deployments, and the jobs and other things. So if we go ahead and preempt and migrate, that's possible in Firmament, but that's not directly supported. So if you kill and if you try to reschedule it on some other node, then you would actually end up messing up the logic of the controller. So that is something we need to get from the Kubernetes side. So that was one of the things. So you can follow us here. So quickly, if you have any questions on Poseidon, so can we take it afterwards, like after you're done? Yeah. Yeah.
Okay, thanks for the Poseidon part. Yeah, and for now we have default scheduler, we have Kube-batch and Poseidon. This is a common question to me how they work together, but I'd like to say, I don't know. We support multi-cluster. We support each scheduler will have the OR of all pod and all nodes. The decision may be conflict, right? And the conflict may be acceptable to the long-running service such as the Tomcat because you just restart the Tomcat or restore Tomcat to the other pod. But for the batch workload, such as for the MPI, if one pod was rejected, the whole job will need to restart. Yes, this is going to be really, restart, scheduling, something like that. So this is going to be really, really long time for things to do that. But personally, I also have some discussion here about the multi-scheduler. Now, the first one is we are going to have a static node for each scheduler. That's going to be the simpler one, I think, this part. Another one is your workload or your storage, your job is acceptable to the current behavior. The kubelet will reject your job, and you will. I think this is fine. If this is fine to your workload, that's fine. Yeah, this depends on your workload and depend on your expectation of this part. Another part, I think some people also propose this kind of architecture. We have a bootstrap. So some result for the scheduler 1, some result for the scheduler 2, but we don't have too much effort on this part because we would like to use the option 4. Yes, we already have what we are going to do right now in the upstream is we have a scheduler framework here. And the scheduler framework has several callbacks to make sure you can customize your behavior, customize your policy or algorithm for this part. So what we are trying to do is that whether we can combine such kind of feature into one scheduler. Now we are trying to the option 4, but there's still lots of effort here. Now default scheduler have a really long history, and Kube-batch we use Kube-batch is the initiative before the framework. So we also have several code, several behavior here, and Poseidon is based on the graph. So this is going to be different architecture or different implementation here. So we also have several things to do that. But at least I give a start here. We would like to do that. Yeah. This is about the scheduler part. Another part, I think this is the descheduler. Because for all of this scheduler, we will not try to reschedule pod if the pod or if your task are already running here, right? So, but after several long time later, your resource utilization will be not good enough, or maybe some predicts maybe break because of some people change the node level, something like that. So we introduce a descheduler to have default scheduler, to have Kube-batch, and maybe some your personally customer scheduler to have a chance to check the results in the cluster again. If they didn't meet your expectation, you just kill some pod. So the default scheduler, also the controller will recreate the pod, and the related scheduler will reschedule it based on current policy or based on the current algorithm for that. So this is the descheduler. Descheduler, for now, descheduler in part several predicts several priorities from the default scheduler. And I think when you try to use a descheduler, you need to make sure the descheduler's decision will consist with the scheduler, either Kube-batch or either default scheduler. Otherwise, the scheduler will make a decision 1, and the descheduler will make a decision 2. They will kind of ping pong, and the pod cannot be finished, or the service are going to be unstable for there. Yeah, this is the overall of the descheduler part. I will not go through one by one, and you can check the list, get the repo. All of this project are in the Kubernetes 6. You can find the Kube-batch, Poseidon, and descheduler. Yes, so this is in the GitHub repo. Yeah, and we also have a deep dive Sig-scheduling tomorrow. And Bobby and me will give more detail about the default scheduler and what our feature tomorrow. Yeah. So this is all from the introduction, and I think this is a question time. If you have any question, any suggestion, both Bobby and me are here, so we can have to answer your question. Yeah. 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 Sorry.
So bin packing is actually a different kind of approach. How?
We also have like least use. For example, default scheduler has like by default uses the nodes which
least resource request priority, right? So yeah.
When you're scheduling multiple pods at the same time, one option which is not a great option is of course to when you want to calculate costs is to consider all permutations of these.
Yeah, exactly. So what we exactly. So we follow exactly the same thing like that is there in the default scheduler. So what we do is we take first we calculate the least priority for the cost. So essentially it is like for an incoming pod we calculate the available resource on the node. So what we calculate is we calculate the fraction of the used resource, and then we take an average of that, and then we balance out with by taking the variance. I think square root of standard deviation. So so it actually gets us the the balancing of the cost. I mean that's a simple.
It's not going to be accurate though. It's going to be
Yeah. Because we do the mean of the CPU and core mem units. So then we take a standard deviation. We take a variance. So it won't be like perfect.
those will not work for. For something like affinity and anti-affinity.
Yeah, exactly.
Something like this.
Yeah. So those are the quantities that is like not a measurable one. So what we do is currently like that is what we calculate the affinities and anti-affinities as a queue-based thing only. So we don't put that in the graph because graph has a problem. We can go up till only like few dimensions. That is more metric thing. That is why your default schedule is much faster. In cases of anti-affinity and affinity. So I think many of the use cases that we get around the machine learning stuff also involves a lot of this affinity cases, but we always try to tell them like don't use affinity with Poseidon and Firmament. So that is when we need to have the solvers that is available in the open source like the Lemon solver and the CS2 solver doesn't actually support those complex graphs. So you can actually create some XOR types of graphs and do the solving, but we need to we can't have that in the open source. Like it's all proprietary stuff. So if the company wants, we can do that.
Key thing with bin packing is cost will
Yeah. So when the flow graph manager actually connects the task EC, that is the equivalence class which it creates first, to the machine ECs. So each and every line you have the cost, right? So it actually calculates the cost based on the number of tasks he has and based on the number of machine nodes he has. So he will assign it there itself, yeah. And the graph solver actually solves that. So you have to write the cost model. So you can actually change how the cost is assigned, and you can actually change the behavior of the flow of the graph. So there is an OSDI paper. You can go to this our website. I mean, like this GitHub.com. In that you have the README section. Under that, you can actually see the links for the original paper by Malte. So yeah, still expressing multiple dimensions is quite a challenge. But yeah, we can, if you have some good graph solvers that can have all these capabilities, then we can do something. We can improve on that. Yeah.
What happens if the resource is temporarily unschedulable? So like you're at capacity for the request.
Yeah.
Does it behave similarly?
Yeah, exactly. So yeah, so the cases where we can actually see that is like, so you see the resource availability currently when you do the scheduling and you send it to Poseidon and he goes and does the binding. By then, say, assuming default scheduler has actually scheduled a pod, that is the case you are saying. So I won't be able
either the default scheduler schedule it
or the resource or the node goes off. Yeah. So this, what happens is, like, this is again because we don't create the pods. So it is up to the controller manager. After we stamp it and we send for the binding, the scheduler actually stays still. He actually gets another information from that controller. So the source controller, which actually creates that, has to actually maintain the life cycle of that pod. Like we don't actually go on reschedule it or do that. So it will be still in the pending state, or I don't know. I think after bind, it should not be in pending state. If it fails, I think it will. The bind itself will fail. So if bind fails, yeah, we retry. But if the bind is succeeded and then there is a problem later, then it is not handled by Firmament, but it has to be handled by the parent controller which created that object. I mean that pod.
But it won't be bound if there is no resource on that.
Yeah, we do the binding. So from within Poseidon, we call the bind call. So bind call is actually tells the API server that this pod belongs to this node, and it has to send an success message. Like otherwise, we retry or we just.
So does it go do like a similar thing to the default scheduler where it has like a timer and then it will?
Yeah, everything is all the bind calls are threaded. Yeah, all the bind calls are threaded, just like the default scheduler, because we don't have to wait for the bind. So the scheduler job is just to assign the pod to the node, and just like default scheduler, you have a go func and you just call the bind inside that. It goes like that. Yeah.
I guess some more question for Kube-batch.
Kube-batch.
How does pod groups, which there are pods, members that create other members in the same group, how does Kube-batch work with these kind of like constructs?
If they are in the same pod group, we will consider we don't know where the pod from. We only consider this pod in the same pod group and do the scaling. It's up to the user to decide how to define the relationship between the pod and pod group. Yeah. For example, for TF job, yes, we also have integration with TF job. We will create two kind of pod. The first one is a parameter server, and another one is worker. And all of them belong to the same pod group, so we will support down scaling to make sure we start together. Yeah. So if the code also belongs to different kind of job or different kind of controller, in scheduling they didn't it doesn't know that. What you can see is that this pod belongs to this pod group, and it will only follow this relationship to do the scaling. Yeah. So it's up to user to decide to give the correct definition.
Does Kube-batch or
several discussion here, or there, and we also have several discussion here is that for the quarter, personally, I think they only define how many pods you can create, right? This should be really large, quarter, and so you can create several pods here and up to scheduler to make the decision. There may be maybe kind of the max length of queue, such kind of that. But I think this is only some idea in my mind. We don't discuss more detail in the upstream than now.
Correct.
Yeah.
So basically, in Kubernetes,
Yeah.
coda is a pod creation time check, not
Yeah.
pod scheduling time.
Right.
So
Yeah.
we have an admission controller that enforces coda
Yeah.
at the time of pod creation, and if pod passes that coda check and is created, then the scheduler picks it up in the scheduler. It's not a scheduler check, basically.
Yeah.
So, you know what I'm saying? So,
Yeah. I thought though, like, oh, I guess the pod gets projected immediately. Right?
Yes,
exactly.
yes,
It's
yes.
never created, but this is usually not great for batch processing pipelines.
Yeah.
Because batch processing pipelines, sometimes you want to have like a queue of these pods waiting for coda to become available to get scheduled.
It's
right?
inconsistent with the, like, if the cluster is out of resources, it's
Yeah.
attacking behavior, right?
Well, cluster being out of resources is kind of fine, but user being out of coda is the issue here.
Right.
So a lot of times, for example, I may go and create a long list of pods that, for
Yeah.
example, use totally they use 100 gigabytes of, let's say, memory, but I have only 10 gigabytes of memory coda. But I want these to stay in the queue
Right.
and gradually get created as memory becomes available and some of my existing running pods terminate. For example, there are some batch workload that finish their work and terminate. I want more of these
Yeah.
ones in the queue to get created. We don't support that today in Kubernetes, but that's the time that we are working on the roadmap. We want to be able to support these use
Yeah.
cases. They're very common in batch processing.
Yeah. Yeah.
I guess what I'm saying is it's inconsistent in that if you have a cluster of like, say, 10 CPUs and
Mhm.
no quota, you can submit this long queue and it will process
Yes.
Yeah.
as
Yeah.
it
But
goes along.
today, if you do that, probably all of those will go through the creation process and get
Yeah.
rejected. A bunch of them will get rejected.
With resources.
Yeah.
If
Yeah.
users are.
Yes, I think we also did. Sorry, we also did have some proposal in the Kube-batch is that we are going to support delay pod creation. Yeah. So yeah.
It's possible. Even if you have a
Yeah.
controller yourself, you can manage it
Yeah.
yourself. But I mean, we don't
Oh.
have a solution, out of box solution basically.
Yeah, yes. I'm trying to do that based on the pod group and in the administration controller to ensure give some phase or some status to the pod group. For example, pod group in queue phase, we will accept the pod in the pod group to create pod.
Yeah.
If this is not in queue, we will reject that. And whether the pod group is in queue or not in queue, it's a make a decision by the scheduler because the scheduler know whether this pod group is, for example, have higher priority or something like that. Because in the culture controller, he cannot control this part. Yeah. But this is only under the discussion and we don't have final decision for right now. Yes, but if we have some kind of issue, we can rise in the scheduling or in the community to discuss the solution for
I
this
think I
problem.
have it.
Okay.
Yeah.
Yeah.
Okay.
Yeah.
So an aspect of
Yeah.
there's also a
Yeah.
this is special cases for GPU scheduling.
Sorry.
Is there any special cases for GPU scheduling?
For now, in both scheduling and Kube-batch, we only support GPU counting. Right? For example, you have 4 GPU and 1 pod. You have 2 pods. Some pods are asking 2 GPU. We will make sure the GPU will not overuse or something like that. But there is some discussion that we are going to support GPU unlimited topologic, something like that. Right now in the upstream, we don't support that kind of feature. Yeah. But we only about GPU. That is what we support right now. I think we don't put much in the scheduling. We only accept the GPU resource from the node. How many GPU are reported from the kubelet by the kubelet or by the device plugin. For example, if you are using sharing, you report 4 or something like that. We only try to aid or sub to the total count, make sure the total resource will not overuse. This is what we are going to make sure in the kubelet. Yes, we don't know to do the other thing.